Okay? And so, starting from scratch here, what is a matrix? Well, a matrix is just a table of numbers. Okay, and we will say matrices have n rows and d columns. Okay, so this is a matrix with 2 rows and 3 columns. And I will call this matrix A. I will say it's in R to the exponent 2 times 3. The way to read this is that it's in the set of matrices with 2 rows and 3 columns. That's what R to the exponent 2 times 3 means. Okay? The set of matrices with 2 rows and 3 columns. It's worth noting that we denoted vectors with lowercase letters with an arrow on top of them, but we're going to denote matrices with just capital letters, like capital A or capital X. Okay? And the first key idea I want you to pay attention to is that we can think of matrices as being several column vectors just placed next to one another. Okay? What are the column vectors here? Well, they could be the vectors 2, -1, 5 and 5, and 8 and -3. Okay, you can think of A as being the result of taking these 3 vectors and stacking them next to each other. Sound okay? All right. Now, again, we're only going to use the properties of matrices and vectors that really apply to us here. The first type of manipulation we will need to work with matrices is addition and scalar multiplication. Okay, so we can add 2 matrices only when they have the same dimensions, that is, the same number of rows and columns. And when you add 2 matrices, the addition occurs element-wise. And by that we mean, for example, 5 here plus 2 here gives us a 7 in that same position. Or -3 plus 2 gives us a -1 in that same position. Okay? Are we comfortable with how to add 2 matrices element-wise? Great. Scalar multiplication occurs element-wise as well. So if I multiply this matrix by the number 2, all it's going to do is multiply each individual element by 2. So like 2 times -1 gives me -2, or 2 times 8 gives me 16. We're comfortable with addition and scalar multiplication? Okay. Now, the more involved matrix multiplication is when you multiply a matrix by another matrix. Okay, and that's where things get a little more messy. Okay? The first key idea is that you can only multiply a matrix A by another matrix B if the number of columns in A equals the number of rows in B. Okay? And so if we say A has n rows and d columns, and B has d rows and p columns, we can do that multiplication because the number of columns in A equals the number of rows in B. Okay? These inner dimensions, that is, these two, need to match. Columns in A equals rows in B. And when that happens and you multiply A by B, the result will be the outer dimensions, that is, n rows and p columns. Okay? And so let's work through a concrete example. If A is this matrix, what is A transpose A? Well, I never defined what A transpose is. First, it's worth noting that A has 2 rows and 3 columns. A transpose is the result of flipping or pivoting A such that the columns of A becomes the rows of A transpose, and the rows of A become the columns of A transpose. And so A transpose will look something like 2, 5, 8, -1, 5, -3. This has 3 rows and 2 columns, and note that I can multiply A transpose A because these inner dimensions match up. columns in A transpose, 2, rows in A, 2. So the result, what is its shape going to be? Yeah, it's going to be 3 rows and 3 columns. Okay? How do we find those 3 rows and 3 columns? Well, we find them by taking the dot products of A's columns, I should say, with the rows of A transpose. Okay, so you can think of A transpose A as being a matrix of dot products. Okay? So what's the number in the top left going to be? Well, it's the dot product of 2 and negative 1 with 2 and negative 1. What does that end up being? 2 times 2 is 4. Negative 1 times negative 1 is 1. 4 plus 1 is 5. What number comes here? Well, it's the dot product of the second row in A transpose with the first column of A. Right? So the dot product of 5, 5 with 2, negative 1 is 5 times 2, which is 10, plus 5 times negative 1, which is negative 5. That gives me a 5. Okay? What number comes here? Any ideas? Starts with a 9. Well, when you say it in English. Yeah. Good. I guess it starts with a 1, but yeah. It's 19. Where did I get that? Well, I got it by taking the dot product of 2 and 1, or 2 and negative 1, with 8 and negative 3. Okay, we don't have to work out every single one, but here's one more example. What number is going to come here? Chirag? Good, 25. Where'd you get that from? Good. It's the dot product of this row with this column. And you get 5 times 8, which is 40, plus 5 times negative 3, which is negative 15. 40 minus 15 is 25. Okay? So we won't work through every single one of these 9 entries, but are we comfortable with how we would figure out all 9 numbers in A transpose A if we had to? Okay, good. Now what I'd like us to do is take a break and look at these 5 properties of matrices. One of them is not true in general. Which one of these is not true in general? Discuss with the people near you and vote at the concept check site. Or not the concept check site, but the question asking site. Which one is not true in general? So, most of the answers are the same. Which one is it? Which is the incorrect statement? C. Okay? Now, one way of thinking about how C is incorrect is just by looking at the dimensions. Okay? Let's suppose A has 5 rows and 7 columns. To be able to multiply it by B, how many rows must B have? 7, good. How many columns must it have? Could have any number, right? The result will have, since these inner dimensions are the same, we'll have 5 rows and 2 columns. Now if I try and do the opposite, B times A, well then the inner dimensions don't even match. Okay? But let's suppose I choose a number of columns for B such that I could do the multiplication. If B is 7 by 5, well then A times B will be 5 by 5. But B times A wouldn't be 5 by 5, it would be 7 by 7, which is different. Okay? So A times B can't in general be equal to B times A because they don't even have the same dimensions, even when you can calculate them both. Sound okay? All right. Now, I want to focus in particular on matrix vector multiplication. Okay? A vector you can think of as being a special case of a matrix just with one column. So a vector in Rn, that is the space of n-dimensional vectors, is just a matrix with n rows and one column. Okay? Now, what I want us to do is, again, really understand the dimensions that need to be present for us to multiply a matrix by a vector. So let's suppose A is a matrix with n rows and d columns. What must the dimensions of V by? V must be so that we can multiply A by V with V coming on the right. How many rows and columns must V have? Karen? Yeah, it should be D by 1 if it's going to be a vector. Right? That needs to happen so that the inner dimensions are the same. That means V must be in the space of d-dimensional vectors. Okay, good. So this involved right multiplying A by V, because V is on the right. What about if we want to left multiply A by V transpose? Well, A is still going to be n by d, but what must the dimensions of V transpose be? It's going to be 1 by something. What must that something be so that I can do V transpose times A? N, good. Because if I put an n here, well then, again, the inner dimensions will match up. What that means is that V transpose should be a row vector with n elements in it, but it means V should be a column vector with n elements or components in it. Okay? This sort of dimensional analysis will be important. Okay, and it's, again, the kind of thing that you got exposure to in yesterday's group work. Okay, hopefully you're seeing how closely related yesterday's group work was to today's lecture. Okay, good. Now, what I want to focus on is interpreting the results of matrix vector multiplication, because this is going to be super important as we start to tie linear algebra back to regression. Okay, so there's two perspectives on which we can take, or two ways in which we can interpret multiplying a matrix by a vector. One interpretation is that multiplying a matrix by a vector involves taking the dot product of every row in the matrix with the vector. Right? Note that here A has 2 rows and 3 columns, and V has 3 rows and 1 column. Which means that while V is a vector with 3 elements, A times V will also be a vector, because when the 3's collapse, we're left with 2 by 1, but it's going to be a vector with just 2 components. Okay? So you can think of multiplying A by V as being this operation that moves V from being in 3-dimensional space to 2-dimensional space. Okay, and how do I do it? Well, I do it by taking the dot product of V with every row in A. So, what's the first of those dot products? Well, it involves taking the dot product of 2, -1, and -5 with 2, 5, and 8. What is that number? Well, it's 2 times 2 plus negative 1 times 5 plus negative 5 times 8. Okay, this looks like 4 minus 5 minus 40, which looks like negative 41 to me. Okay? And that came from here. What's the second element here? Well, it comes from taking the dot product of v with negative 1, 5, and negative 3. What is that dot product? Well, it's 2 times negative 1 plus negative 1 times 5 plus negative 5 times negative 3. To me, that looks like negative 2 minus 5 plus 15. Last I checked, that looks like 8. Okay? And that came from taking the dot product of v with the second row of A. So the key idea here is that one way of thinking about the product AV is that it's the vector that results from taking the dot product of V with every row in A. Do we agree? Okay, this will be important to remember, taking the dot product of V with every row in A. It's going to come up shortly. Another perspective that we can take on matrix vector multiplication is that it's a linear combination of the columns in A using the weights in the V vector. I'm sorry that the projector is all glitchy here. But here's what I mean. When I took those two dot products on the previous slide, these two numbers were always multiplied by the same number. What was it? 2, right? These two numbers were always multiplied by the same number. Which was it? Negative 1. And these two were always multiplied by negative 5. Okay? What that means is the product AV can be written as 2 times this vector plus negative 1 times this vector, 5, 5, plus negative 5 times this last vector, 8, negative 3. Okay? And note that this is a linear combination of the columns of A. And that's a big result. We're going to think about matrix vector multiplication a lot in this way. Now, this is not anything different than we saw in the previous slide. Like, it's not like evaluating this expression gives you something different than we saw before. It still gives you the same two-dimensional vector, negative 41 and 8. It's just another way of thinking about where the negative 41 and 8 come from. Right, this vector comes from taking a linear combination of 2, negative 1, 5, 5, and 8, negative 3. And remember, a linear combination of vectors is just a sum of terms of the form number times vector. Right? That's what I have here. Number times vector, plus number times vector, plus number times vector. Okay, if I changed the elements of V, I would change the coefficients on these three column vectors. If I change this to a 14, that would change this coefficient to a 14. Sound okay? Now, more generally, I want you to remember the fact that when you multiply a matrix by a vector, what you're doing is taking a linear combination of that matrix's columns. Okay, so this is just a more general form of what we saw in the previous slide, where, there's water on my screen, when I multiply A by V in this case, and here A has n rows and d columns, and V has d rows and 1 column, what you're doing is producing a new vector that results from taking the first column in A and multiplying it by V1, those colors match, plus the second column in A and multiplying it by V2, plus so on and so forth, the dth column in A multiplied by the last element in V. Okay, this is just a more general version of what we saw in the previous slide. And just to stress, this is just another way of writing the mathematical result you would get if you just plugged in numbers for all of these A's and V's. And so this result is a vector in how many dimensions? What's the dimension of AV? N, right? Because remember, here the inner dimensions match up. I have a D here and a D here, which means the output is going to be the outer dimensions, n by 1. Or a n-dimensional vector. Sound okay so far?